Now that we've talked about static fluids, fluids that are not flowing, it's time to talk about flowing fluids, so allowing them to move from place to place at some rate. So to start with, we will assert that if a fluid flows from point A to point B, its mass is conserved. So that is, we're going to end up with the same amount of stuff at one end that we put in at the other end. So this is, we already know mass is conserved, but we're going to use this to derive an important equation. So mass is conserved. We can't create or destroy stuff in this process. And we're also going to assume that in whatever system of flow we have, we are not going to have mass building up in one place. So this is meant to represent, the flow of fluid through something like a pipe or a series of valves or a river system, rather than like filling up a tank or something. So we're saying we're going to be looking at the kinds of systems where we don't have buildup of mass. If we do have a system with a buildup of mass, like flowing into a tank, then what we're about to say isn't necessarily true. But if there is no buildup of mass, and if mass is conserved, then we know that if we put some mass into one end of our pipe, we have to get that mass out of the other end of our pipe, or whatever the pipe is meant to be. An example here. So if we put in some mass, we have to get that same mass out. And if it takes some amount of time to do this, the rate that we put mass in, mass over delta T, is equal to the rate we get mass out, the mass out over delta T. Okay, so for a pipe or river or whatever fluid flow system we're talking about, I'm going to draw it as a pipe as an example, but this works. This should work for anything. So if we have a system with flow like this, we have our fluid moving with some velocity, v, right? So we have our fluid at this part, and the fluid is moving at some velocity. In real life, the velocity might change from one part of the pipe to the other. This is called a flow profile. That's a big deal if you're really interested in fluid dynamics. We're going to assume the velocity is the same at every point across, across this pipe. So what we would call a uniform flow profile. Not the most realistic, but makes the calculations for us simpler. You could also just think of this as like the average velocity, if that helps you swallow this. So this pipe also has a cross-sectional area A. So if you slice through this pipe at any point, you get a perpendicular slice, I should say. You get an area of A, and this pipe is the same area throughout. Okay, so if this is true, then the mass flow rate, that is the mass per time that we have flowing, is equal to the product of the area and the velocity. So A times V times rho, the density of our fluid. So the density of the stuff in the pipe, and we're assuming the density is the same everywhere in this piece. Okay, so this is our flow rate, rho AV. The fact that our flow rate in equals our flow rate out means we can use the following equation, rho in A in V in. So this is the mass flow rate in, and this has to equal the mass flow rate out, rho out, A out, V out. And all of these can change, right? Our fluid can have a different density from one end to the other. The pipe can change size, the velocity can change, but these flow rates have to be the same. All right. This constraint is called continuity. Sometimes this is called the continuity equation or the continuity of flow equation. And this works for any substance, liquid, or for any fluid, meaning liquid or gas. Okay, so for something like a liquid, so if we're talking about water flowing or gasoline flowing, we know one additional piece of information, and that is that for liquids, our density rho is constant, and that is because liquids, for Physics 106, we're considering as incompressible. So if we push on a liquid, we don't change how much volume it takes up, so our density rho is constant. So what that means is that rho in is equal to rho out. We have the same variable on both sides of this equation, and those cancel. So therefore, we get the following simpler equation. A in, V in is equal to A out, V out. So this is for liquids, and this is just saving us one variable step. A times V, each half of this, A times V, this is also a flow rate, but this is not a mass flow rate. This is a volume flow rate. So whereas if we calculate rho times A times V, this gives us some kilograms per second of water or air or whatever flowing through our system. Just A times V is going to give us a volume flow rate that's going to have units, SI units, of cubic meters per second. All right. Great. So both of these equations are important. I think the best examples I can talk about are for the simpler liquid equation. So looking at this relationship, we have some system where the velocity changes depending on the area of our flow system. So in other words, if I have some system where there is some liquid, we'll say water, flowing in, and this is some bigger area, and then our tube or whatever gets smaller. So this is A in, this smaller area A out over here. In order for these two to be the same, if this is our velocity in over here, for A in V in to be equal to A out V out, if A out gets smaller, V out has to get bigger. So we make our pipe or whatever smaller on this end. That means the velocity of the fluid has to be much, much higher. This is a nozzle. This is how nozzles work. So on a hose or something like that, in the hose, the water's moving at some velocity. And if you don't have a nozzle on the hose and you try to spray the water, it's going to go a couple feet because the velocity is relatively low. If you screw a nozzle onto there, all that it does is make the hole smaller. Another way of making the hole smaller, of course, is to cover up the end of the hose with your thumb, literally cover up 90% of it with your thumb. And making that area smaller has the effect of making the velocity higher. And so from the nozzle, you can shoot the water out with a higher velocity, and from what we know about 2D kinematics, that can make the fluid go further through the air. With a higher velocity, the projectile motion gives it more distance. I should say that kinematics-wise, fluids, in the absence of friction-y forces or air resistance forces, they're going to follow the same kinds of trajectories as any particle. So if you shoot fluid at some velocity, at some angle, it will follow the same path as a ball thrown with that velocity at that angle. So we already know why spraying the water faster out of the hose makes it go further. And this is, of course, how squirt guns work also. You can do the opposite. You can have a small area go to a big area and cause fluid flow to slow down. This is useful in things like jet engines, but it's called a diffuser, and there's less. It's less obvious why that's useful, so we won't worry too much about that. Nozzles are kind of the most important application of this here. What's neat to me is just how simple this is. Like there are no moving parts in a nozzle. It is just the getting smaller that makes the velocity higher.